All right, everybody, so I'm going to jump into some work with Newton's laws. We're going to take a look at a classic physics example. That's what the device I have here is for us to do. And we'll see how all of this forces and acceleration stuff come together. As a reminder, next week we will have our second physics exam. On this exam will be questions pertaining to objects in static equilibrium, that is to say objects that are not moving, objects that are in dynamic equilibrium, meaning objects that are moving but under zero net force, and objects that are accelerating, meaning not under equilibrium, but a case of dynamics, and that's kind of what we're going to be looking at today. Before we jump into it, we remind ourselves, what are we doing here? We are studying forces and interactions. Why do we study forces and interactions? Because once we have a complete knowledge of the forces that are present, we can make predictions about the motion an object undertakes, and our predictions should be fairly accurate. We've taken a look at maybe a half dozen different forces, right? Last time we were here, we looked at drag force and we looked at gravitational force. Those two forces are what we would consider non-constants. Why are they non-constant? Well, they have several variables that will change throughout an object's motion. If you think about the gravitational force, right, it depended on the distance between two objects. But if those objects changed in distance, they got closer, that force would increase. So gravitational force is what we would call a non-constant force. If we think about the drag force, right, that depended on how quickly an object was moving. Well, the faster and faster an object moves, the larger the drag force becomes. That is a non-constant force. And if you think about the spring force we saw in lab this week, the spring force in lab, well, the further the spring stretched, the larger the force becomes. All of these are non-constant forces. And why is that an issue? Well, that's an issue because when we take a look at Newton's second law, a non-constant force will lead to the right-hand side of this equation being non-constant. Mass doesn't change usually. So non-constant force leads to non-constant acceleration. And that's a problem because if we think back to the kinematics we were dealing with, the kinematics we've dealt with were all constant acceleration kinematic equations. The constant acceleration kinematic equations, such as y equals initial value of y plus v initial t plus 1/2 the acceleration t squared, right? That applied only when the acceleration was constant, meaning this applies only when force is constant. That is important to understand. We also have another kinematic equation. The speed is given by the initial speed in the vertical direction plus acceleration in the vertical times time. These are our two kinematic equations. Yes, there were more of them. If you look back at that note card, there will be 3 more of them to be precise. Those 3 equations stem from these two. These are your basic 2 kinematic equations for constant acceleration motion. And these will only apply to an object that is, well, under constant forces, meaning unchanging forces. So what do we do then? Well, with springs and drag force and even the universal gravitation force, for those cases, we would have to take a different approach than Newton's laws. So what we discussed today is limited in its applicability. Keep that in mind. But for certain cases, when we talk about Newton's laws, they become extremely powerful. And Newton's laws are extremely powerful when we talk about constant forces, unchanging forces. And that's what we're going to focus on today, unchanging forces. What I've set up here is a very commonly used physics example called the Atwood's device. I'll spell it out. We're going to examine the Atwood's device because the Atwood's device is a very useful device to be created. It's a very useful device to be created. And it leads us to a very nice estimation of like constant acceleration motion. So our Atwood's device is comprised, essentially, of two masses. We'll call it M1 and M2. We have two masses, and they are tied together with a string that rounds itself around a pulley. If you look up here, I have one mass on one side, one mass on the other, and they're connected with a pulley. As one mass goes up, the other falls, so on. So we have our Atwood's device, a very commonly used machine. We understand, to some degree, how an Atwood's device behaves just through intuition. For example, oh gosh, they got all tangled up. There we go. For example, if I had more mass on one side, so I put more mass on the left side, well, what do we expect to happen? Yeah, that behaved exactly how I expected it to. One of the masses fell. All right. So we reset our Atwood's device. Right through. Oh my gosh, this knot become too small. All right. So we have our Atwood's device, and our Atwood's device, I need to retie the knot, will fall to whichever side is heavier. Well, we can analyze the Atwood's device physically by taking a look at the forces at play and building free body diagrams from that, and then predicting accelerations. And from those predicted accelerations, we should be able to figure out some information about how quickly this device will use. And towards the end, I'll give you real-world examples of Atwood's devices and how they come into play. So the first thing we are going to do is we are going to keep things arbitrary. We're going to keep things arbitrary to understand the motion that is occurring, meaning that I'm going to keep it in terms of M1 and M2. I'm not going to put in how much mass I have present until the very end. When we take a look at this, we will make an assumption. And a moment ago, I put extra mass on the left-hand side. This will be M1. So we're going to make the assumption M1 is larger than M2. I'll show you what happens if the opposite is true. But we'll keep this to be the assumption. And when we look at this, we can create free body diagrams. Anytime you're dealing with a physics problem, it can be helpful to create free body diagrams for objects of interest. In this case, we'll look at M1. When we look at mass 1, what forces are present? Tension and weight. Weight points in which direction? Down. And tension points in which direction? Perfect. We have tension and we have weight, but specifically weight subscript 1. I put the subscript there to indicate to me that this is associated with mass 1. Sound good? All right. Well, tension, there is no equation that says tension is this value. Tension always takes on a value depending on what interactions are going on in the system. So we don't have an equation for tension, but weight we do have an equation for. Weight we have an equation for. Last time we said weight is the gravitational interaction. Well, of course, that's universal gravitation constant g times mass of the object times mass of the Earth divided by the radius of the Earth. But that's going a little bit too far, because whenever we're near the Earth's surface, we can always estimate weight to be m1g. And this is useful because we take a look at, then we ask ourselves, does M1 change? No, mass doesn't change. Does acceleration due to gravity when you're near the Earth's surface, does that change? No, it's a constant that we've been dealing with all semester so far. So does that mean weight 1 is a constant or a non-constant force? It's a constant force. Since it's a constant force, Newton's law will apply. So that's wonderful, that checks off. Newton's law will apply to give us a way to calculate acceleration, which can tell us things like displacement. We look at mass 2. And we ask, mass 2, that's the mass that's on the right side of our Atwood's device. Mass 2 has what forces acting on it? Tension and weight 2. Tension and weight 2. Weight 2 goes downwards. Tension goes upwards. Our free body diagrams look identical to each other with the exception that one of them uses mass 2 for weight 2 and one of them uses mass 1 for weight 1. But they do look very similar to each other. And in fact, we look at those T and we say, well, that tension is dealt by the same string on either side, right? It's the same string on either side. Since it's the same string, that means the tension is going to be equivalent between the two values. So what do we know? We know that these two tensions have equal values. This is a force pair. It's a force pair because they have equal values. So this gives us our free body diagram. Now I'm going to introduce another step that we haven't done so far. When we have these Newton's laws example where an object will undergo some acceleration, meaning we are not in equilibrium, it can often be helpful to us to take note of the direction the acceleration is going to be in. And if mass 1 is larger, would we expect mass 1 to accelerate up or down? We'd expect it to accelerate downwards, absolutely. This is coming from this first assumption. So I'm going to put a little arrow there and say acceleration. Acceleration is downward there. What about on the other side? What about mass 2? Which way would we expect that to accelerate? Might accelerate upwards. So we say, okay, mass 2, we'd say that would accelerate upwards. Does that sound good? Okay. Feel comfortable so far? Questions out there, comments, concerns? All right, well, we know the tensions are the same. That's going to be convenient. I want to know something about the motion. We've discussed this before. Whenever you have two objects tied together, if we take a look at it, if it's moving slowly, will they both move at the same speed? Yeah, they're moving opposite directions, but they're moving the same speed, right? Because it moves fast. They both move fast, right? So they share same speeds. They also share same displacements. If mass 2 falls by 1 meter, if mass 1 falls by 1 meter, mass 2 will have raised by 1 meter. They move the same distance. They move the same distance. They have the same speeds. Opposite directions here, of course, but they have the same speeds. So they share those motional quantities. Well, coincidentally, they also share the motional quantity of acceleration. Anytime two objects are connected to each other, they will always share the same motional quantities of velocity, displacement, and acceleration. So I know their accelerations are going to be of the same value. That's why I don't bother to put a subscript here. If they had different values, I might call the one on the left A1 and the one on the right A2, but it doesn't matter because they'll be the same value in magnitude. Opposite direction, but same magnitude. Sound good? So now at this point we start to implement Newton's laws. What does Newton's law say? Well, Newton's laws say that the net force acting on an object is given by mass times acceleration. Yes, and this is a vector equation. What does this mean? This means it's true in the vertical, it's true in the horizontal. Well, there's no horizontal motion to worry about, so we're only talking about the vertical here. So we take a look at this and we say, well, this is going to be true. That tells us that our net force in the y direction is equal to mass times acceleration in the y direction. And you can apply Newton's laws both vertically and horizontally once per every free body diagram. We have two free body diagrams here, so we can apply it 2 times. We say we apply it to free body diagram for mass 1, and it's going to tell us our vertical forces, tension minus weight 1. Why did I put the negative there?
It's going down.
What's going downwards? The weight, the force, right? Doesn't have to do with the acceleration. The force of weight is going downwards. That's why the negative is there. We say that that equals mass times acceleration. Why did I put the negative there? What was that, Brian?
Acceleration's in the downward
Ac-
position.
Acceleration is downwards. So I put the negative there to indicate a downward acceleration, just like when we were dealing with free fall problems, right? When we were dealing with free fall problems, I might put minus half gt squared with negative to indicate downward acceleration. So we put that negative in there to indicate the direction of our acceleration. We do the same thing on the mass 2. We say tension minus weight 2. The negative there to indicate the direction of weight 2 is equal to, this time, positive mass times acceleration, positive MAY. Why positive? The acceleration is upwards. It's absolutely correct. So we implement our signs there to indicate directionality. Does this seem okay? Any thoughts and comments and concerns? All right. Now, there's something missing. What mass are we talking about here? Right, I just put in M. I didn't specify what mass. So we look at the left equation. Tension minus weight 1 is equal to negative what? M1 or M2? M1, absolutely. So you say tension minus weight 1 is equal to negative mass 1. Tension minus weight 2 is mass 2. When you apply Newton's second law, you want to make sure that the mass you are discussing is the mass of the system identified in that free body diagram. The mass of the system identified in that free body diagram. In this case, my free body diagram just represents single masses. This can be different. This can be looked at in different ways. So we get these two equations. We apply Newton's second law once per each free body diagram that is present. Once we have it applied to each equation, we then take a look at this as though it were just an algebra problem, M2A plus. Okay. We look at this as though we're just an algebra problem, because typically when you set up and create an Atwood's device, you would know how much mass is present. You would know M1, you would know M2, meaning you fully would know the mass and the weight of each object. The unknowns in an Atwood's device are going to be the tension and the acceleration. Those are the unknown values. The tension and the acceleration. Well, in physics, we do these force problems because we want to know about motion, right? We want to know about the motion of an object. So typically, if I were to create one of these Atwood's devices to do something for us, I want to know the motion. Does that mean I care about what the tension is? No. I don't care what the tension is. Tension is whatever it is. It has a value. Certainly we can calculate how much tension there is, but I don't really care what it is at this point because I want to know about the motion of the problem. So, I say, I want to algebraically remove this tension force from these equations. How do I do that? Well, I do that by first solving one of these equations. What am I going to do? Weight 1 minus M1A. I solve one of these equations for tension, just like what I've done here. I think I did that correct. And then I'm going to plug it into the bottom equation, where we have weight 1 minus M1A, plugging in for the tension, minus weight 2 is equal to M2A. Does it sound good? So we go through and then we say, yeah, I want to know what the acceleration is. So I'm going to do a little bit of algebra. Weight 1 minus weight 2 is equal to M2A plus M1A. So just moving that M1A to the other side, do some simplification. And what you would find is that the acceleration is equal to weight 1 minus weight 2 over mass 2 plus mass 1 for our values. So let's look at some examples. If mass 1 is 60 grams and mass 2 is 50 grams, then my question is, what is the acceleration? Well, the acceleration is going to be weight 1 is m1 times g, minus weight 2, well, weight 2 is m2g, g is 9.8, typical 9.8 value. Remember, we always use positive 9.8 for substituting into that g. Negative 9.8 is put in there for directionality purposes when we deal with free fall problems. Then we go divide this by m1 plus m2. Well, plugging values in, we have 60 grams times 9.8, and I'm not going to bother doing a unit conversion. I'll show you why in a second. 60 grams times 9.8 minus 50 grams times 9.8. And we divide that by m1 plus m2. I'm just going to do the 110 grams. Now, why don't I do my unit conversion? Why don't I bother here? It's because it's grams on top, it's grams on bottom. It'll cancel out. It doesn't matter if you use grams, kilograms. Actually, if you wanted to convert it to the SI unit of a pound or a stone, you could do that as well, but I'm not going to bother. You get the same result no matter what. Doing a little bit of math. I'm going to do the algebra real quick. So 60 minus 50 would be 10 grams over 110 grams multiplied by 9.8. Or you could do 1 over 11. 1 over 11 times 9.8. What do you get when you do 9.8 divided by 11? What is your acceleration? Was it? 0.89 meter per second squared. All right. So you take a look at this. I'm going to swap them around. On the right-hand side, I have 60 grams. On the left-hand side, I have 50 grams. I drop it. And ask the question, well, did that look like it was about 0.89 meters per second squared? And the answer is, well, I have no idea. Right? Intuitively, what is acceleration? Intuitively, it's hard to tell what acceleration is. It's hard to look at an object and be like, yeah, that was about 0.89 meters per second squared. Like, it's hard to have that intuition. You ask the question, well, why is that? That's because acceleration is based off of speed, right? It's based off measured speed. Well, technically measured velocity. And velocity is taken off of measured distances. Distances are something we're familiar with. Speed is an abstract, Speed is abstracted out from position, and acceleration is abstracted out from speed. So it's like an abstraction of an abstraction. It's harder to tell. So instead what we are going to do is we're going to take a look, not at acceleration, but ask ourselves a question. We're going to ask ourselves a question. What is its displacement? Something that's easier for us to see. What is its displacement? And this is easy, right? I can take a look at this and I can say, well, its displacement is going to be, well, that looks to be about a meter, if I put it up on there. So I'm going to say, okay, well, it displaces about a meter. So our displacement is 1 meter. Wonderful. That tells us something about its motion. I know it's going to move 1 meter, but can we make a prediction off of this? Physics is powerful because we can make predictions. So I know it's going to move 1 meter. My question is, what prediction can we make? And a prediction we can make is ask, how much time is it going to take to move that 1 meter distance? How much time? No, I didn't mean to do t equals 1 meter. How much time is it going to take for it to move that 1 meter distance? And again, this is the power of physics, because now we can make real-world predictions based on this theoretical mathematics that we're doing. Well, how do we figure out the time? From the free body diagrams, we've utilized Newton's second law, and from Newton's second law, we figure out the acceleration. Now we have the acceleration, the displacement. We can figure out, we have the acceleration, the displacement. We can figure out the time from our kinematic equations. We stitch it all together. We stitch everything we've done this semester together in this way. So we implement. Our kinematics. We say our displacement delta y is equal to v naught y times t plus 1/2 acceleration time squared. Our initial velocity, well, I released it from rest, meaning our initial velocity is what? 0. So delta y is equal to 1/2 our acceleration times time squared. I know my acceleration. I know my delta y. We can solve this. 2 times delta y divided by acceleration, square root. That should give us our time. So from our theory, we make a prediction. How much time will it take for our Atwood's device to move 1 meter? Go ahead and solve this out for me. We have 2 times 1 meter divided by 0.89 meter per second squared. That'll give us our time. So we calculate this time. This time is a prediction. It's a way for us to predict something that will happen in our reality, in our universe. We calculate out this prediction and we find that the time should equal what? What do we get? 1.5. 1.5 what? Seconds. 1.5 seconds. Does it sound like what we all got? All right, so then we test it. We see, does it actually match up with reality, or have I been gaslighting you this entire lecture? Let's see. Let's break out our phones, pull out a stopwatch. We're going to time this, see if it does in fact take about 1.5 seconds for it to travel 1 meter. Okay, we all have our stopwatches ready, yes? Okay, I'm going to count down. I'm going to say 3, 2, 1, go. And on go, you are going to start your stopwatch. And you are going to stop the stopwatch when the lower mass reaches the pulley. Sound good? You're going to see, what do we get? All right, 3, 2, 1, go. Oh. All right, false start, false start. We're going to have to reset. A little bit of a collision there. Let's try this again. Let's get our stopwatches at the ready. We'll give this another shot. All right. We reset our stopwatches. We get ready. 3, 2, 1, go. I did it earlier. All right. Third time's the charm, and if it doesn't work, then, we'll, I don't know, give up and go home early. No, I would never be so kind to you. All right. Okay. One more try. Yeah, it's about a meter. All right. 3, 2, 1, go. This is, I'm going to do something a little bit different. This is going to give us a little bit slower of a time, but got to do what we got to do. Oh, of course it works out. Right. Okay. We'll give it one more try and then we'll do something else. Okay. Need to stop swimming. Stop swimming. Okay. One more try. 3, 2, 1. All right. And we look at our stopwatches. What did we get? About 1.5 seconds? Yeah. Now, is it going to be perfect? No, probably not. Why is it not perfect? Well, it's not perfect because reaction times are being dealt with here. It's tough to get a perfectly accurate measurement, but you should have seen that it did take about 1.5 seconds. Is that what we saw? Yes? More or less, roughly. If we took a class average, it'd probably be pretty close to 1.5 seconds. But hopefully this is proof enough for you to believe that Newton's laws do make predictions about the real world. Bless you. Newton's laws makes predictions about the behavior of actual physical systems. We're going to do another calculation here. This time, we are going to break one of the assumptions that we made during our derivation. Well, what assumption did we make? We made one assumption. What assumption did we make? That mass 1 was greater than mass 2. Well, what if that weren't true? Let's see what happens to our mathematics. Let's say, for example, mass 1 were 50 grams, and mass 2 were 55 grams. What if this were the case? Calculate out what the acceleration is. Share it with your neighbor once you have that value of your acceleration. Raise your hand if you want a little more time. majority rules. We will move forward. What did we get for a value of acceleration? What was the answer? What did you get?
Negative 0.47 meters per second squared.
Negative 0.47?
Yeah.
Acceleration is negative 0.47 meters per second squared. Now, the assumption we made is incorrect. And because of that assumption we made being incorrect, we end up with an acceleration being negative. In fact, this is something that pops up pretty often in physics. If you make an assumption and you end up with a negative value to end with, chances are the assumption you made was opposite of what was true. If we had made the correct guess that mass 2 were falling down and mass 1 were falling upwards, if we made that true statement, we would have ended up with the reverse of our, where we have weight 1 minus weight 2 would have been weight 2 minus weight 1. That's the only difference. So our assumption being incorrect here tells us is found here in this acceleration's negative term. So what do? Well, we could do one of two things. We could rederive everything, or if we understand that this negative comes from that incorrect assumption, we can say that the acceleration here is going to be 0.47 meters per second squared in magnitude, and go back and reevaluate the direction. So all of that is to say the equation works whether mass 1 or mass 2 is larger than the other. The equation works, but you have to have an understanding of which way the acceleration is going to go. And here we just work backwards. We say, well, I know the acceleration is going to be 0.47 meters per second squared, and I know the acceleration of mass 2 is going to be downwards and mass 1 is going to be upwards, and you can go through and make predictions from there. Okay. So we have this idea of an Atwood's device. And what's the point of an Atwood's device? The point of an Atwood's device is that it can tell you about the acceleration, or it gives us a way to predict acceleration of this object with two masses that are going up and down. Now, what use is this? What use is this is that Atwood's devices are used pretty commonly because they provide a nice little counterweight to get an object to raise upwards. This is very similar. This is very similar to how elevators work. Elevators, another fascinating physics example. With an elevator, you have a cab that you would ride up and down through different floors in a building, and there's a mass on the other side, and that mass falls to bring the elevator cab up. And there's a motor in there to provide a little extra force to get it to go either way, but there's this counter mass giving you an Atwood's-like device. And now I want to examine an elevator, but before I move on to that, are there any questions? So again, we are linking this idea of mass and acceleration. So here's what we're going to do. We're going to create a simple elevator. A simple elevator that is an Atwood's device. And inside of this elevator, we will have one side that has a mass, M2, of 600 kilograms, so really scaling this up. And on the left, you have the mass of the elevator cab, a little room you step inside of. So 475 kilograms. And you will have a person inside of the elevator that is 100 kilograms. And we set it in motion, release the brake. And what's going to happen? Is the person going to move upwards, or is the person going to move downwards? I think the person is going to move upwards. We think they're going to accelerate upwards, yes? All right, well, my question is, what is the acceleration going to be? I want you to work with your neighbor to figure out what the acceleration of the person moving upward is going to be. Find the acceleration that the person is going to feel. Acceleration acting on the person. Yes. And I would strongly recommend taking the time to draw free body diagrams. Apply new and second law. Get into the habit of doing that. Yes, it's going to look identical to the Atlas case, but it's helpful to go about this process. Yes.
But then you have so it doesn't really
So we should have found an answer, perhaps, yes? Does anybody want to share what their acceleration they found was?
4.52 meters per second squared.
It's a little bit large.
Oh, alright. 0.21 meters per second.
At 0.21, is that what we got? So that's probably closer to correct. 4 meters per second, that'd be 4 meters per second squared, that'd be fast elevator. But let's go through the process. Let me show you the step-by-step solution here, because it can be a little bit tedious to go through every single step, but I want to show you them anyway. So when we look at this, we want to create free body diagrams. Perhaps we make a free body diagram to represent the mass of the cab. That might be useful, right? Because you want to know, or to represent the cab, because you want to know the cab's motion. Ultimately, that's what we're asking, what is the acceleration of the cab? You might want to make a free body diagram for mass 2, right? The hanging mass. Now, it's important because it'll tell you about the sort of counterweight that is pulling the other object up. Perhaps you want a free body diagram for the person inside the elevator. That might be useful as well. So what we're going to do is create an interaction diagram, go back to the start, create an interaction diagram where we have the person in the elevator, we have the cab, and I'm going to put those nice and close to each other because the person is in the cab. I don't necessarily want to represent that on an interaction diagram, but I want to put those close together because I know they're on the same side. We have the counterweight mass 2 on the left-hand side. And do we have any other objects in our environment or system? The pulley at the top, yeah, kind of. That's going to be a little in the weeds. We'll put it though. We'll put it. We'll have the pulley.
Still have the entire Earth.
You have the entire Earth, absolutely. I heard someone else say that earlier too. What else do we got? Rope. Rope giving tension, right? So here's what I'll say. Rope. And here's why the pulley gets a little in the weeds. It's always going to be in the environment when we put our stuff together. So taking a look, we start to link our different interactions. Person and cab, that's going to be a normal force. Person, entire Earth, gravity, cab, gravity, mass 2, gravity. Gravity goes to the rope, gravity goes to the pulley. I'm going to keep those off just because it's going to get a little bit messy. But gravity does go everywhere. Sound good? We have the rope with the pulley. That is technically a normal force. The pulley is supporting the rope. The rope goes to the cab. The rope goes to mass 2 through tension interactions. Sound good? Now we make a determination. What is our system? What systems of interest do we have? What do we want to analyze? We can make a choice to analyze perhaps the person. I'll call this 1, system 1. I will look at the cab. I will call that system 2. And I'll look at the mass. I'll call that system 3. And again, the pulley does not interact directly with any of the 3 systems, so it's not going to play a role into our calculations, but it is still present. That is absolutely true. So we make our 3 free body diagrams. For the person, system 1, we have what 2 interactions?
Tension.
Not tension. Normal and gravity, right? The normal force of the floor of the elevator pushing up on the person. And we have the weight of the person going downwards. Yeah? All right. Does that feel decent? Is there any questions about that? Go on, system 2. Being the elevator cab, what interactions do we have acting on the elevator cab? We have the tension. That's one. What else?
Weight of the person.
Careful about the terminology here, right? Because the weight of the person, the weight of a person is the interaction between the entire earth and the person. When we use that term weight, we are talking specifically about the
weight of the cab.
well, the weight of the cab is there, that is for sure. Weight of the cab, tension. But that weight of the person is not there. Instead, there's a different interaction between the person and the elevator. What is that interaction between the person and the elevator cab? Normal. That is the interaction there. Normal going up, perhaps? Does that seem all right? What's wrong with that? Normal is perpendicular to the surface. Perpendicular to the floor of the elevator, that could be up or that could be down. Now I marked it here as up, but that's incorrect. Because yes, the elevator is pushing up on the person, but when we take a look at the elevator cab, the person is pushing down on the elevator. So normal force goes downwards. Normal force is not always directly upwards, right? If we take a look at the surface in that interaction pair, the surface feels a force going downwards. So those are our first two free body diagrams. Do we see where those came from? And then finally, we have our third free body diagram. Our third free body diagram being tension up, weight of mass 2 on the other side, or weight 2. Okay, not so bad, right? At this point, what we can do, create 3 instances of Newton's second law. 3 instances of Newton's second law where we say normal force minus the weight of the person, mass times acceleration. I would expect the person to be going up in this case, as we stated earlier, so I'll put a positive there. We have from this second free body diagram, tension minus normal force minus the weight of the elevator cab is equal to mass of the elevator cab times acceleration. And then finally, on the far right side, tension minus weight 2 is equal to mass 2 times acceleration. Now, in these 3 instances, I did make a mistake. What was my mistake?
Mass 2 is not negative.
Well, it's not mass 2 that's negative, but it's the acceleration associated with mass 2 that's negative. So we do need a negative sign there. Why do we need a negative sign there? Because it's going down. Always pay attention to direction. Always pay close attention to direction. Sound good? Okay. Now I'm going to show you something. And that's when you take these 2 equations and you add them together. We're going to take these 2 equations, we're going to add them together. That will give us, on the left-hand side, normal minus the weight of the person plus tension minus normal force. We take minus the weight of the cab. Right? We add together the left side. Then we also add together the right side, which would give us mass of the person times acceleration plus mass of the cab times acceleration. Sound good? Do we see how I added those 2 equations together? And remember, algebraically, you're always free to add equations. There's nothing wrong with that. So you add these 2 equations together, and you'll see that the normal force cancels out. What you end up with tension minus the weight of the person minus the weight of the cab is equal to mass of person plus mass of cab times acceleration. There's a lot going on here, right? And you're going to be upset because there's a lot going on here to get us to a very simple solution that we've already seen. But we go through this process and we end up with this equation, right? Tension minus weight of person minus weight of cab, mass of person plus mass of cab times acceleration. I'm going to claim to you there's a faster way to get here than what we did. And that's by creating a system that is a combination of multiple objects. Because when we looked over here, I said person is system 1, cab is system 2. I could have done something different. I could have said my system is defined by the combination of cab and person. You're always free to combine objects so long as they have the same motional quantities. You're always welcome to combine objects into a singular system. And when you do that, you end up with 3 interactions that cross that boundary between environment and system. What are those 3 interactions? Well, it's going to be tension, the weight of the person, and the weight of the cab. And then you have Newton's second law saying that these 3 interactions, tension, weight of person, weight of cab, must equal the mass of your system. Mass of my system here is the mass of the person added to the mass of the cab, times acceleration. So by defining your system as being a combination of both, you can bypass those 2 free body diagrams and combine them into one. And it's just a little bit of a shortcut. You're always welcome to combine multiple systems. In fact, we can do even a little trickier thing. Because all of these objects, all 3 of these objects have the same acceleration, right? So I'm going to do something even trickier. I'm going to define the system to be the mass of the person, the mass of the cab, and the mass of the hanging mass on the other side. And when we do this, we say, I want to define positive to be upwards in the direction of acceleration, and I want acceleration to match amongst all 3 of these. Since I want acceleration to match all 3 of these, I would define positive to be downwards on the other side. Essentially what I'm doing here is I'm defining positive to be in the direction of acceleration. And when we do this weird combination of each of the 3, we can find that the net force, which is equal to tension minus weight of the cab minus weight of the person plus weight of mass 2. Why is it plus? It's plus because I'm defining downward to be positive on that side. Is equal to the total mass times acceleration. So you define all 3 objects to be the same system, and you have an even further shortcut. Now this is tricky. This isn't always going to be something you want to do. But I'm just showing you that it is possible to combine multiple objects into one system. We combine multiple objects into one system, and what we end up with? We end up with the acceleration is equal to, oh sorry, I forgot one of my tensions. Minus tension there. Tension should cancel out. We have the tension interaction in both places. So you get the acceleration is weight 2 minus weight of the cab minus weight of the person divided by the total mass of all 3 objects. This is exactly what we have with the Outlook's device, just with an added step. And you could have gotten here identically by taking these 3 equations and solving for acceleration. You can get there identically either way, whether algebraically or whether through doing a clever little trick like combining multiple objects into one system. Anyway, most of you were able to do it to find that the acceleration is about 0.2 meter per second squared. And what can you do from here? Well, from here you can figure out how long it takes to go from one floor to the next. How long does it take the elevator to move? But elevators are fascinating. Elevators are fascinating because, here's the thing, you step on an elevator and you start to feel a little different. How many of us have been on an elevator before? Okay, a few of us aren't raising our hands, in which case I would say go find an elevator, step on one. It's an interesting experience because when you step on an elevator and it goes up, what do you feel? You feel a little heavy as it starts to lurch upwards. If it were to go downwards, you'd feel a little lighter for a second, yeah? You feel a little heavier as it goes upwards. Well, why do you feel heavier? Because you have an increase in how you feel weight. How you feel weight. And when we talk about feeling weight, you might be inclined to say you're feeling this gravitational interaction. But that's not true. Because we don't feel the gravitational interaction. No, instead we feel our weight by our body analyzing the pressure on our feet. That's how we feel weight. If you were in free fall, you would feel weightless. Not because gravity's not acting on you, but instead because there's no pressure acting on your body. So instead, when we talk about feeling weight is feeling this normal force. The force on your feet. That is how we interpret weight. We interpret weight through this normal force. So we might call that our apparent weight. Our apparent weight is our normal force. So we ask, this person who has a mass of 100 kilograms, who has a weight of 980 newtons, where that gravitational force is about 980 newtons. This person who has a weight of 980 newtons, what is their apparent weight? Well, their apparent weight can be found from their free body diagram that tells us the normal force, apparent weight, minus the actual weight of the person is given by the mass of the person times the acceleration. Or we would say the normal force, again, the apparent weight, is equal to the mass of the person times the acceleration plus the weight of that person. The mass of the person is 100 kilograms, meaning that the mass of the person times the 0.2 meters per second, that's going to be, 20 newtons? Plus the 980 newton weight? Be 1,000 newtons. Pick these numbers to get that nice round number. But we end up with an apparent weight of 1,000 newtons. So this is to say your feet are used to feeling, for this person, your feet are used to feeling 980 newtons of force. You step on the elevator begins to move, suddenly your body feels 1,000 newtons of force on your feet as you move upwards. You feel a little bit heavier. You feel a little bit heavier because of this increase in normal force. That is where that heavy feeling comes from. You go downwards and your acceleration is negative, giving you a subtracted amount off that weight. That's why you feel a little bit lighter. This is the physics behind why you have that. So, you step on an elevator, you create an elevator with one of these Outlook-like devices, and doing so, you pick a counterweight of 550 kilograms. You pick a counterweight of 550 kilograms. So we set the stage. We set the stage with a scenario. You step on an elevator that has a counterweight of 550 kilograms. My question is, once this elevator's brake is released and you start to move, what is your apparent weight? we start off by asking ourselves, what do we expect? Do we expect that we would feel lighter or heavier in this scenario? What do we think? Why lighter?
Because the cab and the person weight is more than my counterweight.
Okay, so the weight of the cab and the person end up being larger than the counterweight. Why does that mean you'll feel lighter?
Because you're
Someone back here. Why does it mean you feel lighter? Because you're accelerating downwards. Your acceleration downwards. You'll end up with a negative value of acceleration. That negative value of acceleration will give you a subtracted amount off of the original 980. So let's go ahead. Let's calculate the apparent weight. Once you have that apparent weight, call me over and I will check for you if I agree with that value or not. And once you have that value checked off, you're free to head out. Keep in mind, you do have a homework to turn in to me today, yes? I see some people already did. So make sure you turn that in to me before you head out. So this is the last thing we're looking for. What is the apparent weight? The parent weight is the person. So the person plus.
Yeah, it's just
Minus the cap, 475 minus
92.
That's what I was when I had it.
Oh, yeah, yeah.
Okay.
Actually. Alright, so just real quick running through this, what you should see. If you do your calculations, you'll find that the acceleration of the elevator is negative 0.22-ish meters per second. Without rounding, it's 0.217777. So this is the acceleration of the elevator. The apparent weight that the person in the elevator feels is going to be 958 newtons. So this should be the results of what you would find. Gotta practice it some more at home. That does take us to the end of lecture. If you have any questions, stick behind. I am staying here for the next couple hours probably. So feel free to stay behind and ask questions. Otherwise, have a wonderful weekend and turn in your homework before you head out.
I don't know how that
So. You can absolutely add them.